Hello, and welcome to the ASLA online training module focusing on low voltage lighting. My name is Brian Qualls. I will be your moderator for this module. If you have any questions regarding today's module or you have any questions on low voltage lighting in general, please feel free to contact me by phone or by email at any time. Here's the agenda for this module. We've already done the introduction. I'm going to quickly do some definitions. We're going to then talk about voltage drop and Ohm's law, and then finish up with showing you some different wiring method designs. I like to start each class with a picture of a well-designed lighting system, just to show that you can do wonderful things with the low voltage lighting. So let's go ahead and get started and talk about some definitions. When I first started, I really started designing more irrigation systems before I moved into low voltage lighting, and as I progressed into low voltage lighting, I was quite surprised of how similar the principles are in designing an irrigation system and also designing a lighting system. So, of course, in irrigation, we all know that these are the components: spray heads, pipe fittings, point of connection, and our controller in any design irrigation system. On lighting, we've got pretty much the same thing, where it's our fixtures, our wire, same as the pipe, our connections, which could be equated to our fittings. Point of connection is our primary power, and primary power, I mean, is the 120 volts coming out of the house that we plug our transformer into. And then finally, we have the controller, which is our transformer that controls the system. The next definitions we want to get into is watts, volts, and amps. A lot of people get confused or they don't quite understand the difference between the three, but it's very important because there are three different components. So in irrigation, again, we have gallons per minute, pressure, and velocity, three components of designing an irrigation system. In low voltage lighting, watts is about the same as gallons per minute. So watts are the usage of the actual system, what we're pulling out of each lamp. So if a 35-watt lamp is using a lot more energy than a 20-watt lamp. Pressure is the same thing as our volts. So much like in an irrigation system, I've got to have a certain amount of pressure to get that irrigation head to pop up and spray. I've got to have 12 volts in order to get that light to turn on. If I go anything less than 12 volts, I start getting a very dim lamp, and then go from there. And then the amps is nothing more than the resistance on the wire or the velocity of the electricity as it runs through the pipe. So much like in irrigation, I can't exceed 5 feet per second on PVC pipe. The wire, different size wire, has amp load that you cannot exceed. If you exceed those amps, you tend to melt the wire. The National Electric Code states that a low voltage lighting system operates on a system at 30 volts or less. This is important. I know everyone knows that a low voltage lighting system, first thing you think of is 12 volts. And that's true, but according to the National Electric Code, we can go all the way up to 30 volts and still be considered a low voltage lighting system. The reason why I bring this up in this module is we're going to be talking about transformers, and multi-tap transformers will go above 12 volts to compensate for voltage drop. Speaking of the transformer, here is a picture of one, and the transformer really is the heart of the system. It's taking 120 volts out of the wall and converting it down to 12 volts, which is what we're using to run each of our fixtures, run our lamps. And because of it's a 12-volt system, voltage drop becomes an issue on any low-voltage lighting system. And we account for that with the multi-tap transformer, which we'll talk about later in this module. So let's get a little bit deeper into voltage drop and talk about it. So what is voltage drop? Well, here's a long definition, but it's basically the rapid decrease in voltage as a result of several factors. To simplify it for this module, we'll talk about length. So much like an irrigation system, the further I get away from that first valve, I get pressure drops. So I get less pressure at the end of the line as I do at the beginning of the line. Same thing is true with low voltage lighting. The further I get away from that transformer, the less volts I have at the end of that line as I do at the beginning of the line. And then, of course, that equates to less volts means dimmer light down towards the end of the line. So why do we care about voltage drop? Well, as we talked about, we get dim lights. We also shorten the lamp life of each fixture. And then we get an ugly lighting portrait. We've all seen one out there. We've probably seen several. And in fact, here's a picture of one. So as I look at this, I can tell you with great certainty that our transformer is somewhere on this side of the house. And then they've daisy-chained and ran this line all the way down the length of the house here. So as you can see, I'm really, really bright on this side, getting some really good hot spots. And as we slowly go down, we're getting dimmer and dimmer until we're very, very dim on this side here. Now, how do we compensate for that or overcome that? Basically comes down to correct sizing of the transformer and your wires, and then also very important, correct wiring design. Let's take a step into Ohm's law here and talk about how that helps us with voltage drop. So Ohm's law states watts divided by volts equals amps. Now, I use this on every project that I design. As I get the fixtures all laid out and I start figuring out where my wires are going to go, I start running Ohm's law. This helps me with my wire size, my wire length, and my transformer sizing. So what? Well, I get this question all the time. Why can't I just plug these in the ground and let them work? Well, again, let's go back to the definitions in irrigation. We don't just put sprinkler heads in the ground and hope that they work. We need to account for the gallons per minute running through the pipe, the pressure, and we size the pipe correctly. With low voltage lighting, it's the same thing. So we need to figure out again that in order to run this many watts, I've got to have 12 volts without exceeding the amp load for the wire. So let's see how it works. We'll quickly run through this. At 240 watts, if I'm running that on a 12-volt system, so let's say I've got 240 watts on one line, I'm getting 20 amps. If I take that same 240 watts and run it on 24 volts, I'm getting 10 amps. Now, if I were to take the 240 watts and put it on a 120-volt system, so the same wire, the voltage that you're running through your house, I'm only pulling 2 amps. And if I get a 240 volt, I'm only pulling 1. So as you can see, the higher the voltage, the lower the amps. Now, the reason why this is important is when I'm at my house and I'm buying lamps or any type of electronic device, I don't think about the voltage or the amps. I just plug it in. As you saw in the previous slide, it doesn't matter because we're pulling such low amps on a higher voltage. I think a lot of people think the same thing's true with low voltage wire when it actually isn't. Because we're running such low voltage, the amps become a huge factor in making sure we've got enough power running each of those lamps. And here's why, or here's the reason. So if you take a look at a halogen system, according to the manufacturers, you need to be running anywhere from 10.8 to 12 volts in order to get that lamp to work correctly. It's really only a 1.2 volt window. It's a really small target to hit. If I go anything below 10.8, that's where I get those really dim lights. If I go above the 12, that's where I get the real bright ones and they get, the hot spots. And also, too, if I run anything higher than 12 volts, I'm really shortening the lamp life of that fixture. So I may, have to start replacing those every 2 or 3 months because of running them way too hot. Now, since LED has come out, and LED has come a very long way in a very short period of time, they've changed that volt window. As you can see now, and this varies from manufacturer to manufacturer, but on average, you're looking at a minimum of 10 all the way up to a maximum of 18 volts. Now, again, because of the NEC, this is still considered low voltage. But the great thing about LED is that at 10 volts or 18 volts at each fixture, I'm getting the same light output. There's not going to be any difference in light output anywhere in between these two numbers. Now, if I go below 10, that's when the LEDs will actually start to dim. And if I go above the 18, we'll actually short the light, the LED out. It won't get brighter. You'll actually fry the electronics inside that LED. So how do designers compensate for voltage drop? Well, first they'll use larger wire. I'll just put 10 gauge in the ground and that'll work. They limit the circuit length, which means they'll shorten that length coming out of the transformer, but then use more transformers around the properties in order to get the lights to work. They won't do anything at all, and they'll leave it up to the electrician to design it at 120 volts. So we use a multi-tap transformer, but again, it doesn't really help for the voltage drop. At the end of the line, you'll get them all to turn on, but they won't be evenly lit. Lower the lamp load by using LED, which is not a bad thing. In fact, that previous example that I showed you of a voltage drop across the house there, if I were to switch that over to LED, as long as I had anywhere between 10 and 18, that would even out the light all the way across that front face of that house and just change that lighting output dramatically and make it look a lot better and get closer to the intent of the design rather than what you saw in that picture. And here's the biggest problem. Most people don't realize that there's a problem. They put fixtures on a plan, hope that the person that's going to install it is an expert at it, and chances are that person isn't. So we need to talk more about doing low voltage lighting in the design stage of the wiring, and that's what this is all about. I get this question all the time in varying different areas, but to make this for this class, what is voltage drop of a 12-volt, 35-watt lamp that's 100 feet away from the transformer? Well, let's go ahead and work it out. Now, if anyone is interested, I have this sheet here available to anyone that wants it. I have it in PDF and as an Excel spreadsheet. If you'd like a copy of this, please feel free to contact me, and I'll be happy to email it to you. So let's go back and work out our problem. So let's say we're going to have our 12-gauge wire. We've got our 35 watts that we're going to run on a 12-volt system. Now, we're going to figure out the amp load. Watts divided by volts equals 2.8, 2.9 amps. So I'm going to round it up to 3. We're going to be 100 feet away from the transformer. Now, we need to work out to get our voltage drop. We need to work out this formula here. So we take our amp load, times it by our length. We multiply it by 2, and the reason why we multiply it by 2 is we have alternating current. So the electricity is going back and forth, so we need to account for that. Our resistance per foot on 12-2 wire I have down here, 0.00162. And our voltage drop is around 0.9, so I'm going to go ahead and round it up to 1. So the answer to the question of what is the voltage drop of 12-volt, 35-watt lamp is a 1-volt drop. Now you can use that sheet, that formula, for any amount of watts that you want and any volts, and I have all the information that's on there. It'll work for any system, anytime that you want. So where does voltage drop occur? Voltage drop occurs basically everywhere. It's at your power source. Much like a backflow preventer, we usually account for a 1-volt drop inside the transformer. We usually add that at the end there. As we talked about the wire length, so the longer the wire, the deeper the drop. Wire size, we showed the resistance. Change the wire size, changes the resistance. Your lamp load, it's much like irrigation. If I've got a main line that's got one sprinkler head on it, it's going to use less water than if I put 5 on there. Same thing with low voltage lighting. If I put one fixture on the line, I'm using less electricity, creating less voltage drop as if I had 5 or 10 on that same line. And then, of course, all through the connections, and much like an irrigation system, we lose pressure through elbows and 45s. We lose voltage drop through all the connections. And then tarnished wire. I get the question all the time, can I reuse the wire that's already in the ground? If that wire is tarnished, it's much like reusing a clogged pipe. You're not going to get as much carry through of the electricity through tarnished wire as you would through a good brand new wire. Primary power, this is very important. Primary power is not always 120 volts. I know we like to think that, but it really isn't. It changes throughout the day, and it changes on the usage throughout the part of town that you're in. I usually like to recommend that landscape architects put a note on their plans that says that the system was designed assuming that we have 120 volts at the primary point of connection. And the reason why is that our transformers, there's nothing electronic inside of them. They are just basically a 10-to-1 ratio. So they only put out what they take in. So as an example, if I'm putting in 120 volts, I'm pushing out 12. So with that, if you had 100 volts going into the transformer, what would the voltage be on the 12-volt tap? If I do the 10-to-1 again, 10 divided by 100, I would only have 10 volts coming out of that tap. Again, that is why I recommend putting that note that the system has been designed based on 120 volts. So if that changes, the contractor can then adjust accordingly out there in the field. Been talking about the multi-tap transformers. Here is an illustration of what the taps look like. So we've got the two commons over here on the left, and then taps go up from there. So on our transformers, they go up to 22 volts. And as we talked about for NEC, it's still considered low voltage lighting because we're under the 30. And then here's a picture of that transformer. So these are the actual taps, commons on the left, 12 going all the way up to 22 to the right. And that's how we compensate for that voltage drop throughout the system. Finally, we're going to talk about the different wiring methods. So again, much like irrigation, we've adopted several different wiring methods to account for voltage drop. Daisy chain method, T, loop, home run, hub, and telehub. Now the first three you've seen in probably every single different irrigation design. So as we go through the daisy chain wiring here, this is the picture of the illustration of that first picture that we had of the house. So I've got proper voltage at the first hub, and then as we go down to the first light, and as we go down, you can see that the voltage is dropping to the point to where we get very, very dim lights on the end. So another way to compensate for that is to do a T method, much like irrigation. So now we have minimized that voltage drop coming up from each end and going that way, which is a better design than the daisy chain method. The loop design here, we see this in irrigation to kind of, again, boost that pressure on the end. Same thing, boost that voltage on the end of the line. Again, we're not getting even voltage throughout the line. I'm not a big fan of this because we're essentially putting more wire in the ground. And unfortunately with wire, someone can easily nick it with a shovel and not even realize that they've done it. And then thus turning this into a daisy chain. Different with pipe. You know, if I hit a pipe, I'm going to know it, and especially if I turn the system on, I'm going to have water spread everywhere. Problem is you don't see electricity if we cut this wire. And then finally, there's the hub method. This method here is probably one of the best for voltage drop. Essentially what you do is you have one home run coming out of your transformer to a hub, and then you set up to 5 fixtures of equal length coming out of that hub. And what that does is gives you equal voltage drop across all fixtures. So as long as I've got 13 volts here, and if I've got these a certain length away and get these down to 12, or if we're doing a LED system and get these down to 10, but they're equally volted all the way across, I've simplified the connection and I've created one run back to the transformer. Now, since the LED is really taken over and voltage drop in LED is minimized, we can now do an IntelliHub method, or essentially basically what we've done is taken a trunk hub and set that up here and then run satellite hubs off of the trunk hub. So I can plug 5 fixtures into here and then do the same. And what I've done now, I've taken 5, 10, 15, 20 lights and turned them back into one home run back to the transformer versus 4 different home runs back to the transformer. Now this system only works on LED. If you try to do it on a halogen system, you'll be disappointed and never get the voltage drop to work. It'll just be too great coming out of this hub. That's the end of this training module. Again, if you have any questions, please feel free to contact me at any time. And thank you for your time.